Applications of systems of linear equations. In this section, we talk about two objectives. One, curve fitting. There we are given a set of points and we need to determine the polynomial based on those points. So we can use linear algebra for that. Secondly, networking analysis, which has the gamut of so many applications, uses a fundamental principle in mathematics and also in physics, and that is the amount of energy that flows into a system has to equal the amount of energy that flows out of the system. That system could be anything. It could be traffic, it could be fluid flow, it could be electricity, uh, and so the application is rich. So first, let's consider polynomial curve fitting. Here, we're given endpoints. And in given endpoints, the polynomial would be a function n minus 1 degree less than the number of points. From there, we should be able to write the polynomial after we've solved the system. The polynomial form that we're going to use is based on this formula here. Let's look at a problem. Here we're given 1, 2, 3, 4 problems. And so if that be the case, then that means that n is equal to 4. So the polynomial that we assume for the approximation would be of the third degree. So here that is, assume p of x is equal to, let me write it down here, so assume p of x is of the form a naught plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x to the third. You count up the terms, 1, 2, 3, 4. We have 4 terms. The degree is 3, n minus 1. So for the first point, negative 1 comma 2, here we're going to try to build a system. So we have basically p of negative 1 is equal to, so I'm going to just replace the x with negative 1. So I have a naught minus a sub 1 plus a sub 2 minus a sub 3 is equal to 2. And then for the next point, 0 comma 0, we have p of 0, where we have x, I'm going to write 0. So all we have here is just a naught, and that's equal to 0. Because the a sub 1 times x is 0, the a sub 2 times x squared is 0, and the a sub 3 times x cubed is 0. The next point, 1 comma 1, here p of 1 is equal to a naught plus a sub 1 plus a sub 2 plus a sub 3 is equal to 1. The last point, 4 comma 52, so p of 4 is equal to a naught plus a sub 1 times 4, we'll just say 4 a sub 1 plus a sub 2 times x squared, that's 16 times a sub 2 plus a sub 3 times x cubed, 64 a sub 3 is equal to 54. Now from this we should be able to write the matrix. So the matrix would be of the form, and here we're considering this. So we have 1, negative 1, 1, negative 1, and 2. Here we have 1, 0, 0, 0, and 0. Here we have 1, 1, 1. Just writing the coefficients, and 1. Here we have 1, 4, 16, 64, and 54. So now we're going to reduce this matrix using Gauss-Jordan form, and whatever we have, if we have values over here in that far right column, then we have the values for a naught, a sub 1, a sub 2, and a sub 3, and then we can write the polynomial, plot the points if we need to, and also look at the graph. So with that, I need to write this on the next page, and I cannot remember it. I thought I could copy this and throw it over. Da, da, da. Let's see. Okay, so this matrix is 1, negative 1, 1, negative 1, 2, 1, 0, 0, 0, and 0, 1, 1, 1, 1, and 1. One, 4, 16, 64, and 52. Okay, so we have a 1 at A11, so that's good. We want to get zeros below that. Since this second row has a leading 1, and then zeros elsewhere in that particular row, then we can flip rows 1 and 2. That is, interchange rows 1 and 2. Okay. So now we're going to use this 1 to get zeros below it. So we're going to say negative times row 1 plus row 2, negative times row 1 plus row 3, negative times row 1 plus row 4. Row 1 stays the same. Here we get 0, negative 1, 1, negative 1, 2, 0, 1, 1, 1, and 1, 0, 4, 16, 64, and 52. Oh, very good. So now we move to A22. We need a leading one there. So negative 1, that's close to it. We're going to use that negative 1 to get zeros below it. We already have a 0 above it. So there we're going to say row 2 plus row 3, and then 4 times row 2 plus row 4. So rows 1 and 2 will stay the same. So this becomes a 0, this is 2, 0, and a 3. This becomes a 0, a 0. So we're saying 4 times row 2 plus row 4. So this is 4 plus 16 is 20. And then 4 times negative 1 is negative 4 plus 64 is just 60. And then 4 times 2 is 8. And then that 8 plus the 52 is 60. Okay. So what I'm going to do is, with that last row, I'm just going to divide everything by 20, and so that just makes those numbers a little bit smaller. At the same time, we can multiply row 2 by negative 1 to get that leading one here at A22. Let's see if I can write that 6 a little bit better. So I'm going to say negative times row 2 and then 1 over 20 times row 4. So row 1 stays the same. I'm negating row 2, so this is 1, negative 1, 1, negative 2, 0, 0, 2, 0, 3, 0, 0, 1, 3, and 1. Oh, excuse me, 3. So those numbers are small, just the way I like it. So now we're going to move to this third column, third row, with at A33. That's where that 2 is, and we want to get a 1 there. By getting a 1 there, that'll give us a fraction over there. Now we may, eventually have a fraction, but if we can save that fraction to the end, let's do that. So I'm going to swap rows 3 with rows 4 because there's already a 1 there. So row 3 interchange with row 4. Okay. So now I'm going to use A33 to get zeros above it and below it. So to do that, we simply say row 3 plus row 2. That'll give us a 0 here. And then negative 2 times row 3 plus row 4. Now row 1 stays the same. So I'm adding row 3 to row 2. So this is 1, 0, becomes a 4, and that's a 1. It's a 0, 0, 1, 3. Row 3 stays the same. And then we say negative 2 times row 3 plus row 4. So this is 0, 0, 0. Here we get negative 6 plus 0 is negative 6. And then we get negative 6 plus 3 is negative 3. Now for that last row, we can go ahead and just divide by that -6. So -1/6 times row 4. That is, we can multiply any row by a non-zero scalar. I'm going to rewrite rows 1, 2, and 3. This is 1, and that's a 1/2. So now we use the 1 at A44 to get zeros above it. So -4 times R4 plus row 2, and then -3 times row 4 plus row 3. So row 1 stays the same. Now I'm going to have the identity or that Gauss-Jordan form on the coefficient side. That's the 1/2 there. So we're saying -4 times that 1/2. So that gives us a -2 plus that -4 times a 1/2 is -2 plus this 1 is a -1. And then -3 times this 1/2 is -3/2. And then we add that -3/2 to that 3. So we have -3/2 plus 3. That gives us 6 minus 3. It gives us 3/2. So let's see what we have. This implies then that we have A0 is equal to 0, A sub 1 is equal to -1, A sub 2 is equal to 3/2, A sub 3 is equal to 1/2. Okay. So let's see how that looks in terms of the polynomial. That is, P of x is equal to, so we have that A0 is 0, so then that's -1 times x plus 3/2 times x squared. I don't like it when I can't write the whole thing in one straight line. Okay. So P of x, that's not a c. So here we get -1x plus 3/2 x squared plus 1/2 x cubed. Well, that's the polynomial. Now, in terms of the graph, you just take those 4 points that they gave us and just plot those on the xy plane. That's very easy. Here's just a rough guesstimate of it, if you will. The first point is -1, 2. Say -1, 2. Let's say somewhere there. And then 0, 0. 1, 1, and then 4, 52 way up here. So if we kind of put everything together, and if we were using calculus 1, you'd have a relative, it looks like a relative minimum probably at 0. And this guy's a little bit fatter than that, by the way, because of how quick those numbers rise up to get to that 52, that last point, 4 comma 52. So, uh, but it's not difficult in web assignment to determine. They're going to give you like 4 graphs, and you have to determine which one. And so that's a better um, scale there. Well, it's not that good actually if you think about it. Look at how they're doing for the x units. 1, the length of 1 is greater than 10, so that's really wrong, right? In terms of how they're scaling that, so that's not fair. So that is definitely skewed, but that's probably the best choice that you have there in WebAssign. The next thing we consider is network analysis. For network analysis, the amount of energy, whether it's, it should be force, and where this force could be, some kind of energy, electricity, fluid, traffic, etc., flowing into a network, must equal the energy, that same energy, to flow out of the network. We consider the nodes or the junctions, and you can kind of add up and subtract from those nodes. Those nodes would represent the entry and exit points of the flow. Cherkov's law is pretty good in physics and also in electronics, dealing with, and I believe it's his second law, that considers um, uh, the amount of electricity that flows into a circuit has to sum up to the amount of electricity that's flowing out of that or away from a particular junction. Let's first deal with this idea of network analysis with respect to traffic flow. This figure shows the flow of traffic, vehicles per hour through a network of streets. So here we have these nodes. I don't know how come it doesn't let me write. So if we consider this is A, B, C, and D, you could say A, B, C, D. It doesn't matter. So first it says solve the system. So we're going to solve this system based on looking at node A. The traffic that comes in has to equal the traffic that goes out. Well, the traffic that's coming in is the 400 plus the x sub 2. That has to equal to x sub 1. Then you move to B. What goes in is 300, but what comes out is x sub 2, x sub 3, and x sub 5. At C, what goes in is x sub 1, what goes in is x sub 3, what goes out is 600 plus x sub 4. And then at D, what goes in is x sub 4 plus x sub 5, and what comes out is 100. So once we set that up, you should have a system there that you can solve. So let me write that out again. So we look at, I think I call that A. Oh, that's lame. B, C, and D. So for A, what's going in, oh well, that's small print, is 400, and that's going to be plus x sub 2 is equal to x sub 1. X sub 1 is the only thing that's going out of A. Then we go to B. What's going in is 300, and what goes out is x sub 2 plus x sub 3 plus x sub 5. We look at C. What goes in is x sub 3. I think that's the only thing that's going in C. And so then what comes out is 600 plus x sub 4. We look at D. What goes in is x sub 4 plus x sub 5. And what comes out is 100. So now we have a system. We just solved this guy. So here's how we're going to write it. Well, I better write it as a system first again. Simplify that. So this x sub 1, this is that first equation, minus x sub 2 is equal to 400. And then that second equation is x sub 2 plus x sub 3 plus x sub 5 is equal to 300. The next one, x sub 3 minus x sub 4 is equal to 600. See, I'm basically just getting the variables on one side and getting the constants on the opposite side. Then that last equation is done for us. X sub 4. I didn't say done forest like a forest or Forrest Gump. I said the last one is done for us. My southern tongue kind of gets twisted sometimes, and the words kind of all go together. So now we can write this in a matrix. So this is x sub 1 is 1, x sub 2 is negative 1, and it has 5 of these variables. So this first equation does not have x sub 3, does not have x sub 4, does not have x sub 5. That's equal to 400. Second equation does not have x sub 1. So notice we're only writing the coefficients. We're not saying that x sub 1 is equal to 0. We're saying the number times the variable, right? That's 0. So here, this is 1 times x sub 2. This is 1 times x sub 3. No x sub 4. 1 times x sub 5 is equal to 300. The next one, there's no x sub 1, x sub 2. There's x sub 3. X sub 4 is negative 1. No x sub 5. 600. No x sub 1, no x sub 2, no x sub 3. We have x sub 4, x sub 5, 100. Now we solve, right? So we want a 1 here, we have it. We want zeros below it, we got it. Move here, we want a 1 at A22, we got it. So we need to have a 0 above it. So simply we can add row 2 to row 1. So in doing that, we're going to have 1, 0, 1, 0, 1. Then here we get 700. Rewrite everything else. I'm only going to do 3 problems today. And these 3 problems take like forever, right? Sheesh. So now, after that, we need to have I wonder if this highlighter works. We need to get a 1 at A33. We have it. And so now, from there, we need to get zeros above it and below it. Well, we have 0 below it, so to get zeros below it, above it, excuse me. So we say negative times row 3 plus row 1, comma, and then negative times row 3 plus row 2. So let's see here. Rows 3 and 4 stay the same. So since I'm simple-minded, I'm going to just rewrite those first. So now row 3 plus row 1. So that's 1, 0, 0, 1, and 1. It's negative 600 and 700. That's a 100. So now negative times row 3 plus row 2. So this is 0, 1, 0, 1, 1. And this is negative 300. Okay. So now, according to Gauss-Jordan, we want to get a 1 at A44. We have that. We're going to get zeros above it. Okay. So to do that, we'll say negative times row 4 plus row 1, negative row 4 plus row 2, and then simply add row 4 plus row 3. And the only row that's staying the same, staying alive, is row 4. So I'm going to put that guy down there. So negative row 4 plus row 1. So this is 1, 0, 0. That becomes a 0. And, oh, where was I? That becomes a 0. That becomes a 0. And this is a 0. Okay. Something went berserk somewhere. And go back and check all this. So that's 400 plus x sub 2 is equal to x sub 1. X sub 1 minus x sub 2 is equal to 400. That's good. We get 300 is equal to x2, x3, x5. x2, x3, x5 equal to 300. That's good. Something with haywire, and maybe you caught it, and that's good. Let's see here. X sub 3 for the C. X sub 3 is going in. That's what it is. Doggone it. X sub 3 plus x sub 1 is equal to 600 plus x sub 4. X sub 3 plus x sub 1. X sub 3 plus x sub 1 is equal to 600. X sub 3 plus x is equal to 600 plus x sub 4. I better check this guy while I'm here. See, x sub 4 plus x sub 5 is equal to 100. Good. So it looks like that third equation so this is x sub 1 plus x sub 2 minus x sub 4. X sub 1 plus x sub 3 minus x sub 4 equal to 0. So see that guy, so it should have been a 1 here. So it's 1, 0, 1, negative 1. Yep. So let me just erase everything else because I'm really mad, right? Maybe it's good that you see this so you can catch your mistake. How did I know that there was a mistake? That's a good question. Um, when I looked at this problem, there's like a part A, part B, and the part B talks about let x sub 3 equal to something, let x sub 5 equal to something to determine x1, x2, x sub 4. Now, when it does that, that begs that the system was probably infinitely many, and at the rate where I was going, I was probably going to get something to not maybe a unique solution, but it was going to be almost close to it. So um, I knew something was off there. So and you know I worked the problem before too, right? So um, I don't know where my papers are where I worked it. I should have been following that, right? But I don't do that. I try to just work things again from scratch, just to kind of show you, um, hey, this is real stuff, right? So, and sometimes you see our mistakes, and it kind of helps you, hopefully. Um, Learn from your daddy's mistakes. But anyway, so let's see here. So I'm going to take this one here and get a one, a zero at um, uh, A31. So let's say here negative times row 1 plus row 3. But it sure does hurt, when it doesn't work out, especially this is being recorded and time is very limited. Your time is precious as well too, and I need to understand that. Um, so negative times this negative 1 is 1 plus 0 is 1. 0 plus 1 is 1. That's just negative 1 and 0, and this is 200. Okay, now rewrite that last equation, that last row. Okay. So now what we want to do is to get a 1 at A22. We have that, so we need to get zeros above it and below it. So to do that, we'll say simply row 2 plus row 1, and then also negative row 2 plus row 3. So it looks like row 2 is staying the same. Excuse me. And so that's row 2. See here, add row 2 to row 1. So this is 1, 0, 1, 0, 1. And that's 700. Negative row 2 plus row 3. So this is 0, 0, 0, negative 1. This is negative 1. and then this is negative 100. Just rewrite row 4. Now you see how rows 3 and 4 are multiples of each other? Well, that begs infinitely many solution. So here's what we do. We say row 3 plus row 4. Now when we do that, we have 1 0 1 1 0 1 1 0 1 0 1, and this is 700 0 1 1 0 1 300 0 0 0. And while I'm doing that, if it's okay, I'm just going to go ahead and negate row 3 to get rid of those negatives. So and we did the addition before that. All right. Well, there's not much we can do with that. So if you look at what you have, if I look down the main diagonal, right, what this says is that I have a leading one for A11, I have a leading one for A12, but for A33, that is for the x sub 3, it's going to be a floating term. Anytime we get on the main diagonal, we get a 0, then that lets you know that you're going to have a parameter there. So that is let x sub 3 equal to r or s or t or what have you. And it looks like the same thing here, but that's not the case because I get a value for x sub 4. So what I'm going to do is rewrite this equation, and basically, if you did that, you would have this row interchange where these zeros are, but Gauss-Jordan says any rows of all 0 you just group to the bottom, and basically you just you get rid of it. So here there's nothing wrong with that x sub 4, but the x sub 5 is strange. It's a floating term. So I'm going to write this out, and you're going to see what I'm talking about. Let me write this out. Okay. So what we have is just put back what we have: 1 0 1 0 1 700 0 1 1 0 1 300 0 0 0 1 1 100. Now let's write this out and see how this looks. Now we already know that x sub 3 is going to be a parameter, but let's see how everything else works out. This is x sub 1 plus x sub 3 plus x sub 5 is equal to 700. That second row is x sub 2 plus x sub 3 plus x sub 5 is equal to 300. That last equation is x sub 4 plus x sub 5 is equal to 100. Notice that the three equations, all three of them depend on x sub 5. That's a parameter. And then we already said that x sub 3 is a parameter. So what that means is that we say let x sub 3 equal to s and x sub 5 equal to t. So if that be the case, now I have x sub 1 plus s plus t is equal to 700. So that implies that x sub 1 is equal to 700 minus s minus t. The second equation, x sub 2, and a lot of times you can look at the equations there and see, what variables depends on another variable, right? So here x sub 2 plus s plus t is equal to 300. This implies, yes, that x sub 2 is equal to 300 minus s minus t. X sub 3 is equal to s. Now for x sub 4, we get x sub 4 plus t is equal to 100. That implies that x sub 4 is equal to 100 minus t. And x sub 5 is equal to t. Okay. So you have it there. So the solution set, and let me put a page in here so you can see that. So the solution set would be x sub 1, 700 minus s minus t, x sub 2, 300 minus s minus t, x sub 3 is s, x sub 4 is 100 minus t, comma, x sub 5 is t. Okay. Now there was some other questions with that. Let me go back up here, knowing that we have that now. That's what we just got through. Uh-oh. That's not supposed to happen. I was trying to circle that. So we just got through solving this. Now the next one says find the traffic flow when x sub 3 is equal to 0. That is, x sub 3, remember, is s, and x sub 5 is t. So starting back with what we had 700 minus s minus t, comma, 300 minus s minus t, comma, s, comma, 100 minus t, and then t. So if we let x sub 3, which is equal to s, if you let that equal to 0, this is part B, and x sub 5, which is t, they're saying let that equal to 50, then what's the point? You see what I'm saying? What's the point? Like, yeah, like give me a calculator. But anyway, this is 700 minus 0 minus 50 is 650. 300 minus 50 is 250. S is 0. 100 minus 50 is 50, comma, t is 50, right? So that's that. And then the same thing, let x sub 3 equal to x sub 5 equal to t. That is, let s equal to t equal to 60. So for the first point, that's 700 minus 120, 7, 6, 580. 300 minus 120 is 180. And then s is 60. 100 minus 60 is 40. And then s equal to t, and they're all equal to 60. So that's all they're saying there, right? Okay, good. Woo. One more problem. It is possible to use linear algebra to solve for the amount of amperage that's flowing through the circuit on each so-called, if it's a resistor. A very simple circuit board here with just a resistor and I believe a battery. So we can use Kirchhoff's law. The amount of current that flows through a circuit is conserved. That is, the sum of the current that flows into a circuit is equal to the current flowing out of the circuit. The sum of the voltage drops equals the sum of the voltage rising. Points 2 and 3 are somewhat already worked for you with these problems in this particular book. In the previous book, it was not the case, and so you had to actually determine the signs of the voltage drop or the voltage rise, and also determine the sign with respect to the resistor, if it was positive or negative. But basically, the resistors do exactly what they do. They resist. So if the current is opposite the flow, if the current that's flowing from the battery is opposite of the flow that's set by the circuit, then we say that there's a voltage rise on the resistor. Just the opposites for resistors. If the current is flowing in the same direction as the direction for the resistor, then you have a drop, a negative. That's for the resistor. But for the battery, if the current that's flowing in the circuit is in the same direction of the voltage, then you have a rise. And if it's opposite, if the current in the circuit is going in the opposite direction of the voltage flow, then you have a drop in voltage. But those two are worked out for you. So when I was looking in this new book that we're using, I said, "Oh man, they got everything worked out." So it's really not too much for the student, but just add everything up. Really, that first one is going to be on this guy here, on that first one, and I'll show you that, and that's the easiest one. So pretty cool stuff. So let's see. So if we take this problem and put the answers up there, but we got to work this dang on thing, right? So these nodes are important as well. Here we go again. Why is it doing that? Oh boy. So this is A, B. I don't know if I'm going to ever refer to them as A and B, but so I guess I could consider. Let's look at A And we're going to look at the flow of the current with respect um, to these circuits here. Basically, these three resistors, I1, I2, and I3. I don't know if you can tell, but here there's an arrow going that way, and here it looks like the arrow is going that way, and then for this guy the arrow is going this way. Sorry, it's so small. So looking at A, I can consider based on these three um, resistors for this circuit board, I can use Kirchhoff's law, that first point, to determine the energy going into this node A versus the energy going out. So if I look at what's going in, that's going to be I sub 1, and it looks like here I sub 3. And what's going out from A is going to be I sub 2. Now you don't have to do it for A and B. Just do it for one of them. If you do it for B, you get the same equivalent. So here, so again, I got what's going in is I sub 1 and plus I sub 3. And that's going to be equal to what's going out. So remember, you go back to that traffic flow problem, right? La la la. So was that I sub 1 plus I sub 3 is equal to I sub 2. And my writing did improve after I erased that, right? But anyway, okay, so after we do that, then here comes the easy part. Again, I told you that these problems are kind of rigged, and with the old book, you get to determine the plus and minus. For this is already set up to be plus for you. So we're going to consider this first loop, and then after that, we'll consider this bottom loop. So if you consider this first loop and look at what we have in terms of the battery and the resistors that's on it, right? So let's see, the the energy that's on the resistors will have to equal the voltage drop on the battery. So that's basically Kirchhoff's law. So here I'm going to have 4 I sub 1 plus 3 I sub 2 is equal to, and they say that V sub 1 is 3 volts. You see that? So we get 4 I sub 1 plus 3 I sub 2 is equal to 3. And then look at that loop on the bottom. That's going to be 3 I sub 2 plus I sub 3 is equal to the voltage drop on that battery, V sub 2, that's 4. So this is 3 I sub 2 plus I sub 3 is equal to 4. Now we just write this as a matrix and we solve it, and we go home. Oh, we're already at home. Oh yeah. Well, okay. So I sub 1 is 1. I sub 2 is going to be negative 1. So I'm just getting everything, all of these capital I's on one side, and this I sub 3 is 1 here, 0. The next equation here, that's 4, 3, 0 equal to 3. This is 0, 3, 1 equal to 4. And we'll just solve that, and that should be it. So we use A11, which is a 1, to get a 0 below it. So negative 4 times R1 plus R2 so 0 here. 4 plus 3 is 7. Now we need to get a 1 where that 7 is. So instead of just dividing by a 7, which we have fractions over here, I'm going to just do this. I'm going to say negative 2 times row 2 plus row, well, that's row 3. Sheesh. Why do I keep wanting to write 2? Negative 2 times row 3 plus row 2. Hey, that'll give us a 1 right there. That's pretty. That's pretty. Pretty good. So let's see here. Row 1 stays the same. Row 3 stays the same. So this is 1. 0, that's 1. We get negative 2 times 1 is negative 2 plus negative 2 minus 4 is negative 6. And then here we get negative 8 plus 3, negative 5. Alright. Now we use A22 to get zeros above it and below it. So we can do that by just adding row 2 plus row 1, and then negative 3 times row 2 plus row 3. So row 2 stays the same. I'm just adding row 2 to row 1, so this is 1, 0. Excuse me. Negative 5, negative 5. Here's a 0, 0. Here we get 18 and 1, we get 19. And then we get negative 3 times negative 5 is 15 plus 4, we get 19. Alrighty, so I need to go to the next page. Let me write that down so I know. Hadn't figured out, and what is this? PowerPoint, how to copy an image, doing everything brand new, teaching from home, and don't have my regular setup at the office or at the college, so things are different. Okay, so here's what we have: 1, 0, negative 5, negative 5, 0, 1, negative 6, negative 5, 0, 0, 19, and 19. So we can just divide by 19 for that row 3, that is multiply row 3 by 1 over 19. And so now we'll use A33 to get zeros above it. So we'll say 5 times row 3 plus row 1, and then 6 times row 3 plus row 2. Well, that gives us the identity matrix here, and the work is over on the augmented side. So this is 5 times 1 is 5, minus 5 is 0. And then this is 6 times 1 is 6, minus 5 is 1. So that implies that the amperage on the first resistor is 0 amps. A sub 2 is 1 amp. A sub 3, 1 amp. Okay. Well, folks, that'll do it. My time got thrown off at one problem. I had to go back and try to fix it. So that was kind of a joke. But hey, we still met the time of class time within an hour and 15 minutes. So an hour and 5 minutes, and probably would have been an hour and 1 minute if I didn't mess up. But anyway, you all take care.